we're going to take a deeper look at binary classification. So the reason we're doing this is we're just focusing on a particular problem that's binary classification, and that's to try to build up our intuition about machine learning and make connections to the concepts we've learned in probability and statistics. There's a lot more to know about machine learning, far beyond the scope of this class, but with this probability foundation, you're very well equipped to go and take some of those more advanced classes. So binary classification is really closely related to this idea of binary hypothesis testing that we've studied before, okay? The key difference is that we do not have, so we're not provided with any conditional probability models. So we don't know what the observation is going to look like under either hypothesis, right? We just have a data set. So instead, we're just going to be given a data set, and it's going to have labeled examples. So we might see under each hypothesis some examples of what the observation ought to look like, but that's it. So we could use these examples as a basis for estimating the underlying probability model, okay? But we don't really care about that. What we care about is designing a good decision rule, okay? And whether or not that involves designing a probability model is up to us. So here's some examples. The first is just design a classifier to tell apart dog images and cat images. The next is to design a classifier to tell apart MRI tumor images that are either malignant or benign, all right? And maybe the data set that I have there is labeled by expert radiologists. Another implicit example is I want to design a machine that automatically sorts harvested fruit, say oranges, into quality bins. So maybe I want my lower quality oranges to go in for juicing, and then I want my higher quality oranges to be for eating, and I want to measure their weight, their radius, and maybe take some other measurements and then make that decision. Okay, well, let's build up a framework for doing this. So we're going to start out with what we're given. So we're going to assume that someone, maybe it's us, has collected a data set, which is really just a collection of labeled examples. Okay, and we're going to write this in the form x vector of I and yi, and I goes from 1 to n. So we have n examples. X vector is a d-dimensional vector, and each entry is called a feature. This is called a feature vector. So if you think about those oranges, maybe one feature is the weight, another feature is the radius, and so on. It's whatever I want to put into my decision-making process. Yi is the label. We're going to assume that it's either +1 or -1. Here's an example of a two-dimensional data set. I'm going to draw some pluses and minuses in this 2D space. So this is a two-dimensional feature space. So you can think that it has coordinates for each example xi1 and then xi2, right? And then if there's a plus, that means that that particular example at those coordinates has a +1 label. And if there's a red minus, that means that particular example at those coordinates has a -1 label. And the reason I'm doing this is just so that you have something to hold on to and visualize as we introduce these concepts, keeping in mind that we usually, when we apply this, we're thinking about a much higher dimensional space where it's impossible to visualize everything that's going on. So our goal or our task is to design a classifier. And in our old language, this was a decision rule. And we're going to call this D with this input vector X. All it does is output either +1 or -1 for any possible input you put in, right? And you can design this using the data that you have. So here's just one sample. I just drew this purple line. Above the purple line, I said blue, so decide +1. Below the purple line, I said -1. And that's just kind of an arbitrary drawing. I'm just trying to give you a visualization. And we're going to measure the performance of our decision rules or our classifiers using the error rate, okay? And that's just going to be the fraction of misclassified points. All right. So in this example, we have 20 examples, and we misclassified 4 of them. So I kind of made some mistakes here so you can see what's going on. So the error rate is 4 out of 20, and that is 20%. And it's pretty common to see these things reported as percentages. You might also see the complement. So you might see the accuracy, which is just how the fraction I got correct. In this case, that would be 80%. But we're going to stick to error rate because that's a lot closer to the probability of error concept that we saw earlier in the course. Okay, well, remember, one of our first tasks is that we need to split our data set, okay? So we have a data set, we really need to split it into training data and test data, and these should be separate examples. So here, if I have n examples, so n feature vectors x and their labels y, I'm going to take them randomly and put some of them into this training set, which I'm going to call x train I and y train I. I'm going to get n train of those examples. And the rest is going to go into my test set. So I'm going to get x test 1 and y test 1 and so on up to x test, n test, y test, n test. Okay, I'm circling those in this example in purple for the training data set and the rest in green. Okay, just to give you a visualization. So I have some training and some test data. The training data, x train and y train, and I have n train of those points. I'm using that to design my classifier or decision rule, and I'm also going to use it to tune the parameters of my decision rule. So, if I want to put a certain amount of importance on the weight of an orange versus a certain amount of importance on the radius of the orange and so on, all of those decisions I have to make using my training data. In contrast, my test data, this is written as x test and y test, that is held out. And the reason I'm holding that out is I'm only trying to estimate the real world performance in terms of the error rate of this decision rule. I cannot use this to tune any parameters. And the reason for that is then I might end up making an erroneous estimate of the underlying error rate, because if I tune the parameters using the test data, I'm kind of cheating and using some of the specific features of those test examples to pick my parameters, and that might make my performance better than I actually will have when I'm seeing completely new examples. So really, only training data can be used as part of the classifier design. And just note, just for notation, n train plus n test, the number of training examples plus the number of test examples is just equal to the number of total examples, n. Okay, it's going to be helpful for our purposes to develop a function, and that is going to count errors for us. Now, if you're kind of more familiar with probability, maybe you've seen this idea of an indicator function. That would work perfectly well here, but we're not introducing that concept in this course, so I'm not going to use it here. I'm just introducing a custom function. So my custom function is gerror. It takes in my decision and my true label, and it says 1 if they're not the same. So that means there's an error, and 0 if they are the same. So if they aren't the same, that means the input was misclassified. If they are the same, that means it was correctly classified. So then I just need the training error rate and test error rate definition. So training error rate is just the fraction of misclassified training examples. So then I just take the number of misclassified training points and I divide by the total number of training examples, right? And if I want to write this mathematically, what that means is I just have 1 divided by n train, the sum going from 1 to n train of g error, the training examples against the test examples. Okay, and then if I want to do the same thing for the test error rate, I have the fraction of misclassified test examples, and that's going to be the counting the number of test examples over the total number of test examples. And so that's going to be 1 over n test, and that's summing up from 1 to n test, g error of d x test versus the true label y test. And keep in mind always, we can usually get to 0% training error rate, or we can always do it by memorizing the data set, but that might not be a useful strategy because memorizing it doesn't help us learn any underlying concepts, and then we won't get a low test error rate. So what we want to do is learn something from the data set to make a good classifier that will perform well or generalize well to new data, right? And so that may not come from memorizing it perfectly. And we'll see a little bit of that as we start to play around with these problems, but maybe in the smaller examples that we're visualizing, it's kind of hard to notice that. Let's start with the nearest neighbor classifier as just an example of a strategy we can pursue. Of course, with all of these classifiers I'm going to introduce, there are more sophisticated strategies that are used in practice because they're able to draw on more sophisticated optimization techniques, but we're just using a few things to get you comfortable with how ideas from probability can be used in classification. Okay, so the basic idea here is all I'm going to do is find the training example in my training data set that is the closest to my input vector. And then I'm just going to say that I think that input vector has the same label as that training example. Okay, so I just look at my input vector, find the closest point. So the index of that closest point is the argmin of this distance, this d-dimensional distance between my training examples and then my input vector, okay? And maybe it's easier to see what that looks like if I'm looking over this, length. So I have z, length of a vector, and that's just the square root of the sum of the squares of the entries of z. So if I do that with a difference between x train of I and x, then I'm going to get the, the distance between those vectors, right? And so if I just take the argmin of that, then I'm finding the closest point, and then I just look up its label. So on this plot on the right, what I've done is I've kind of sketched out in red the positions where you would be closer to a red point than a blue point, and in blue, the points where you'd be closer to a blue point than a red point. So there are 12 training examples, and we're not making any errors because when you look up your own value, you always find yourself, and so you don't make any training errors, so you have 0% training error. But what about test error? So here are the test points, there are 8 of them. The number of test errors I make here just happens to be 1, and so the test error rate is 1/8, which is 12.5%. This is a non-parametric classifier because I'm not actually trying to find a probability model, so I'm not basing this on any particular distribution family. I could also consider a k nearest neighbor classifier. We're not going to do that, but it's very easy. All I do is I find the k closest training examples, and I just look at their labels, and I take a majority vote. So if I found the 3 closest training examples, right, and their labels were +1, +1, and -1, I would say +1 is my guess. If I found that their labels were -1, +1, and -1, I would say -1 is my guess. And in that sense, it always makes sense to take k to be odd. And that's something you could play with on your own. We're just going to work with this nearest neighbor with one neighbor classifier. Okay, next we're going to look at this closest average classifier. That's terminology we're just introducing so you remember it. You might hear this referred to by other language in other courses like naive Bayes, but we're just going to call it the closest average. So the basic idea here is that you compute the conditional sample mean, okay? So the sample mean vector, really, of the training data under each possible label. In this case, I only have y equals +1 and y equals -1. And then I find the closest mean vector to the input vector, and I output the label. Okay, so it's basically like this nearest neighbor classifier, except instead of going example by example to find the closest thing, I compute the mean, the center of mass of the training examples for +1, and I compute the mean under -1. And then I just decide which of those two means is the closest to what I see. So I need a little bit of notation. I need to count the number of training examples that have a positive label. And I need to count the number of training examples that have a negative label. So that's going to be n-train plus and n-train minus, right? And so then I also need the indices where I have a positive label, right? So the indices where I have a positive label, +1 and -1. I have the labels where I have a negative label, right? And now what this lets me do is sum up over those positive labels, normalizing by the number of those positive labels, the feature vector, and then I get this mean vector mu hat. So that's an estimate of the underlying mean of the positive examples. In this plot, I draw this with a blue circle, and you can convince yourself that that is the center of mass of these points. I can do the same thing with the negative examples. So I normalize by the number of negative examples, sum up over the examples whose label is negative, and I get this red circle. So then the closest average classifier, all it does is it says +1 if the positive mean is closer than the negative mean, and it says -1 if the negative mean is closer than the positive mean. And I just do this by taking the difference in vectors and taking the lengths to figure out which one is closer. So in this example, here's what that's going to look like. So on the blue part, I'm closer to the blue mean, and the red part, I'm closer to the red mean. The number of training errors is 3. So the training error rate is going to be 3/12. That is 25%. And the number of test examples is going to be 8 the number of errors I make on the test data set is 1, 2. So the test error rate is going to be 2 over 8, which is also 25%. All right, next up we have linear discriminant analysis. This is also a classifier, and it's just building on the idea we had before. The basic idea is to actually assume that given the label, the input vector is indeed Gaussian. And the way the parameters are chosen is that they have separate mean vectors, mu plus or mu minus, and the same covariance matrix, sigma, okay? And so what I need to do is estimate these parameters because I'm not given them. I need to estimate them from my data set. And then I'm going to apply the ML rule, assuming that what's really going on is I have a Gaussian with those mean vectors and that covariance matrix. I'm going to use the same notation from the previous slide. So I have my positive and negative training examples. So I have their positions. So the L's are the indices where I have positive and negative. And then the n train plus and minus, that's the number of positive and negative examples I have. And then mu plus and mu minus hat are the estimates of the mean vector. So what I need to do is estimate the covariance matrix. So I do that for the positive examples first. I use my sample covariance matrix estimator, right? So I just take this outer product of x train minus its mean vector, sample mean vector, okay? I do the same thing for the negative examples. I build an estimator of the negative mean. In MATLAB, this is a built-in function, but I'm just writing it out here for you so you can see it. And then I pool these two estimates together because I believe the covariance matrix is the same. So I just combine them together and I get my estimate of this overall sigma. So then I have this conditional PDF under +1, which is a Gaussian vector. So this is its PDF. So x minus its mean transpose sigma inverse x minus its mean. And the same thing for the negative examples. The only difference is I replace the positive mean with the negative mean. Okay, so this is basically the estimate I form of the conditional PDFs, right? And now that we have the estimate of the conditional PDFs, I'm in a position to use the ML rule. So that's what I'm going to do. I'm going to shift these up. And the ML rule says guess +1 if the conditional mean under y plus 1 is larger or equal to that of that under y minus 1. Equivalently, I can look inside this exponent and say what I need to do is make the term inside the exponent as small as possible, right? Or so basically what I'm saying is if e to the minus z is what I'm looking at. So let's say in this case, it would really be e to the minus 1/2 times z. So if z is small, then e to the minus z times 1/2 is large. So what I need to do is make this term z larger in order for the overall conditional PDF to be, I need to make this term smaller in order for the overall conditional PDF to be larger. So I'm looking for x minus its mean transpose times sigma inverse x minus mean transpose to be as small as possible, and I choose that corresponding hypothesis. I'm going to open up this product. So again, this is not something I'm asking you to do on your own. I'm just kind of quickly opening up this product of terms, right? So it's just like opening up like x minus a squared, but in linear, kind of in matrix vector form. I cross out the two terms that are the same, and I move the x terms over to the right-hand side, and I keep the constant terms over on the left-hand side. And really what I get is something that looks like a vector times x, and I'm comparing that to a threshold c. And this is a linear classifier, so it's just a line. So this linear discriminant analysis says +1 if this vector times x is greater than this constant, which is derived by the positive and negative mean vectors times the inverse covariance matrix, right? So these are just a particular choice of linear classifier, right? I'm just deciding which side of a line I'm on. Okay, and it's -1 otherwise. So the closest average classifier could have actually been viewed as this classifier, the linear discriminant analysis, where I was actually taking the assumption that the covariance matrix is the identity matrix. Okay, that's just a little note that if you want to use this method, and if you went and plugged in sigma equals identity, then you would have gotten something that looks like what we were doing before. All right, so let's just apply this. So I have my line, and I have the top, which is blue, and the bottom, which is red. So I have one training error. So my training error rate is going to be 1 over 12, that's 8.3% approximately. And then my test number of examples is 8. My test errors is 2. So my test error rate is going to be 2 over 8, which is 25%. Okay, and this is a parametric classifier because I'm actually assuming some distribution. I could have assumed that the covariance matrices are different, and then I would have ended up with something called quadratic discriminant analysis. The reason it's called quadratic is you're keeping this quadratic term, which is x transpose times the covariance matrix inverse times x. So that's like a square term. And then you get a kind of a curved decision boundary, but we're not going to cover that here. Okay, so the last thing that I want to talk about is that modern approaches to binary classification that are kind of beyond our scope, what they do is they rely heavily on large-scale optimization techniques. So maybe they're not doing things that you can write down in closed form, but you can still get to the answer pretty quickly with a computer or a bunch of servers. And they're trying to select the parameters of their decision rules from much richer families of functions to deal with massive data sets. Okay, so that's kind of the key difference. So here we're kind of dealing with smaller data sets, 2 dimensions, and we're doing things that we can kind of write down and play with and understand. And you can understand the modern approaches in principle, but really what they're doing is pushing those out to a massive scale. And that's a little beyond our scope because we haven't really covered any optimization in this class, and we don't assume it as a prerequisite. Just as an example, neural networks, what they do is they use gradient descent. So they kind of wander in the direction of the gradient to set the weights of individual units. And these individual units are kind of loosely based on biological neurons, like a very crude approximation of a neuron. So if this is a neuron, right? So here's a picture or a cartoon illustration of a neuron that I borrowed from Wikimedia. And you can see the inputs are coming in, and then you're getting outputs. That's kind of just a rough approximation of how to think about it. And what you can do here is just think of this as a linear function, so b1 times x1 plus b2 times x2, all the way up to bd times xd, followed by some kind of nonlinearity, which makes the decision, if you think about it as a neuron, whether to fire or not fire. Okay, and by the way, this one is actually not a fire or not fire situation. It's a ReLU nonlinearity, which is what's more common in modern neural networks, but we can set that aside. And one thing you might have heard of is deep learning. And the idea there is to use many, many layers of these units to tackle massive data sets. And again, use large-scale optimization techniques to set the weights. And this is beyond our scope, right? So, I mean, here I've just drawn 4 layers. So I had my input layer and my output layer, that's 2, and then 2 hidden layers in the middle, right? But these would have to be much wider and much deeper to kind of get to the scale that I'm talking about in modern use. But just to give you an idea of how this works, let's look at a really simple example, which is the perceptron. So as I said, gradient descent is kind of a little beyond the scope of this class just because we don't have enough time to cover it, not that you couldn't understand it. And I'm just going to implement a really simple variant of the perceptron that doesn't use gradient descent. And the reason I can do this is I can write the answer in kind of closed form. And this is basically the first artificial neural network. Okay, so the picture that you should have in mind here is the same thing as before. You take a sum of your inputs weighted by these b's, and you apply a nonlinearity, which in this case, if you're positive, you say +1, and if you're negative, you say -1. Okay, so that's going to be our perceptron. And the way to do this is I'm going to collect my training data and its labels into a matrix and a vector. So I write my training matrix as these transposed feature vectors, and I write my labels as just a vector of labels. And once I've collected all of those things together, then what I can do is I can just apply my artificial neural network decision rule to be +1 if this particular linear classifier, right, so that I've written here, is larger than 0 and -1 otherwise. And this thing that I've written turns out to be the least squares solution to the following problem. Take the training data set times a vector minus the training labels. So basically minimize the length of that vector. And if you stare at this for a while, you could actually convince yourself that this is the LLSE solution, except I'm using the sample covariance matrix and the sample cross covariance matrix. We're not going to ask you to derive that, but that's exactly what this is. It's basically the same ideas we use from LLSE estimation for vectors, but I'm using the sample versions of the covariance matrices. All right, so that's actually what's happening there. And so just to wrap up, let's just look at this. So it just gives me a linear decision rule. I have one training error. So my training error rate is going to be 1 over 12. That's 8.3%. And then my test errors, I'm just going to have, in this particular case, one test error. And that's going to take my test error rate to be 1 over 8, and that is 12.5%. And the only thing I kind of want to point out here is that the fact that one of these classifiers on this data set was lower than the other, it doesn't really tell us anything very deep. It's just an example to help you follow along what these things kind of look like and help you have a picture to carry with you as we take these into higher dimensions with more interesting data sets.